Hello everyone, in this video let's learn how we can design the circuit for a full adder using NAND gates only. In the previous video we saw the truth table for a full adder which has three inputs A, B, and C in and two outputs, the sum and the carry out. So using NAND gates we can start from the SOP form, sum of product for the sum and for the carry out. So to get the minimal expression for the SOP form for the sum, so let's use K-maps. We have three inputs A, B, and C in, so let's use a three inputs K-map. So on this side, we're going to have A, and then on this side, we're going to have B and C in. So for A, could be 0, could be 1. For A and B, C, and for B and C in, 0, 0, 0, 1, 1, 1, and 1, 0. So let's check where the sum is 1. So it's 1 in this area here for 0, 0, 1. So this is 0, 0, 1. 1 again in this area corresponds to 0, 1, 0. So this is 0, 1, 0 is 1. Again, it's 1 in this area, 1, 0, 0. So this is 1, 0, 0 is 1. And lastly, 1, 1, 1, the sum is 1. So this is 1, 1, 1. And the rest are zeros. So as we can see, we cannot group any adjacent ones together, so they have to remain separate. So the Boolean expression for the sum will be as follows. So from this one here, we're going to get A is 0, so this is A bar for the prime. B is 0 and Cn is 1, so this is B prime Cn plus. For this one here, we're going to get A is 0, so this is A bar. And here we have 1, 0 for B, Cn, so this will be B, Cn bar plus. This one here, A is 1, so this is A. B, Cn are both 0, so this is B bar, Cn bar plus. For this last one here, A is 1 and B, Cn are 1, so this is B, Cn. So this is the Boolean expression for the sum. So next, let's get the Boolean expression for the Cout. Also three variables K-map, so this is the Cout on this side. Similarly, A on this side and B, Cn on this side. That's 0, 1, 0, 0, 0, 1, 1, 1, and 1, 0. So let's check where the Cout is 1. It's 1 in this area, which corresponds to 0, 1, 1. It's 1 in this area, which corresponds to 1, 0, 1. It's 1 in this area, 1, 1, 0. And then lastly, it's 1 in this area, which corresponds to 1, 1, 1. And the rest are zeros. So for the Cout, we can do some grouping. We have adjacent ones, so we can group these two together. We can group these two together. And we can group these two together. Let's use another color. Now we can write the Boolean expression for the Cout. So from the blue, we're going to get A is 1, so this is A. And then from here to here, we have Cn is not changing and it's 1. So this is Cn plus. In red, from here to here, A is changing, so we don't write it down. So in this area here, we have B and Cn are both 1. So this is B, Cn plus. From this group here, A is 1, so that's A. And then from here to here, B is not changing and it's 1. So this is B. So that's the Boolean expression for the Cout. Now from these two, we can design the circuit for a full adder using NAND gates only. So let's start with the Cout. So we have summation. So that means we need an OR gate. So this is an OR gate. And then we have a 3 multiplication terms. So that means we need a 3 AND gates. So this is 1. This is the second one. And this is the third one. And the output is fed into this OR gate. And then from these inputs, we have A and Cn. For the second one, we have B and Cn. And then for the last one, we have AB. Now, how can we convert this to a NAND gates only, which is the purpose of this video? If we have an input signal and then we add NOT gates twice on its path, so that doesn't change the value. If it's 1, we'll have 0 here, and then it'll be inverted again, so the final output is 1. If the input is 0, it'll be 1 after this NOT gate and 0 at the end. So adding 2 NOT gates on the same signal the wire doesn't change the final value. So let's do that here. Let's represent the NOT gate by a bubble. So on this signal wire here, we add it twice, and then same here, we add it twice, and then we add it twice here. Now, if we look into this NAND gate, this AND gate with a NOT gate after it, this is a NAND gate. Similarly for these two, an OR gate was NOT gate on every single wire of its inputs. This is equivalent to a NAND gate as well. So now let's redraw our circuit. So now we can redraw this one. So on this side we have a NAND gate. This is C out. And then here we have 3 NAND gates. And then we have the inputs A, B, and Cn. So A, B, and Cn. For the top NAND gate, we need A and Cn. For the second one, we need B and Cn. And then for the last one, we need A and Cn. So we can take them from here. So this is A, and this is Cn. So let's follow the same thing for the sum. So we have summation, so that means we need an OR gate, and we have 4 terms, so that means it has to be with 4 inputs. So let's just like separate these. So this is an OR gate. The output is the sum. And then we have 4 terms, that means we need 4 AND gates first. And they're all fed into this OR gate. And then for the inputs, for the first one, they're all 3 inputs, these AND gates. So let's draw the input wires first. For the first one, we need A bar, B bar, and Cn. So that's A bar, B bar, Cn. Second one, we need A bar, B, Cn bar. Third one, we need A, B bar, Cn bar. Last one, we need A, B, and Cn. So now same idea, let's add a NOT gate twice on this wire, every single wire of these. So that's it. So now this here becomes a NAND gate, and then every single one of these is a NAND gate. So let's redraw our circuit. So on this side, we have a NAND gate. This is the sum. And then we have 4 NAND gates on this side. And then they're all fed into this NAND gate. And now we have, sometimes we need A bar, B bar, and Cn bar. So how can we get the invert of an input using NAND gate? So if we use NAND gate with 2 inputs, and we feed the same input to both of its inputs. So this is A. So on this side, we get A bar. So we can do the same thing for B. This is NAND gate. We can feed B to both of its inputs, so we get B bar. And then we can do the same thing for Cn to get Cn bar. So this is Cn, and then this input was B, so we get Cn bar. Now let's look. The top one, we need A bar, B bar, and Cn. So we can take A bar from here, B bar, and Cn, we have to take it from before the NAND gate. So this is Cn. For the second one, for this one here, we need A bar, B, and Cn bar. So let's use another color. So for A bar, we can grab it from here. B, we need to take it from before the NAND gate. And C and bar we can take it from here. So same idea for these two NAND gates. We know where to get them. We need A, B bar, C and bar. So we can take A from here, B bar and C and bar from this area. And same for the last one. We need A, B, and C in. So we need to grab them all from before this NAND gate. So this is how we can design the circuit for a full adder using NAND gates only. So this is how we get the C out on this side. And then this is how we get the sum. And at the end, it'll be like the combination of these two. So at the end, it'll be like one circuit inside this box with all NAND gates and 3 inputs A, B, C in, and then 2 outputs sum and carry out. Thanks for watching. I hope this was helpful.
Enjoyed this video? Subscribe to the Computer Engineering Notebook for more tutorials on computer architecture, embedded systems, and hardware design. And hit the bell to catch the next one.